they will still obey the same commutation relations as for the case L is 1. And you can go up as high as you like. You'll still get the same algebra, the same commutation relations result, well, the matrix equivalent as we got for L equals 1. Right? New topic, a big new topic, and basically spin, and many sessions on this. In fact, spin is a really important concept in quantum mechanics, and we'll take that concept up for quite a few levels above senior level, because spin is basic to quantum mechanics. You can classify the particle types into two very broad categories, the fermions and the bosons, according to their spin of the particles. The table of the elements depends to some extent on the spin of the elements. So all chemistry depends on the notion of spin. Particle physics uses spin a lot. Relativistic quantum mechanics, Dirac's equation that we'll come to in M1 level, the concept of spin comes out of Dirac's mathematics. So spin, it's hard to overemphasize the importance of spin. So now we introduce the concept. All right? Now, each author has often a different way of doing that. Like I say, I have dozens of textbooks on quantum mechanics, and you look at each one, and each author has his own take on how to introduce the concept. Well, Davies, he takes a more mathematical analogy type of approach. Like here's his question. Now, all these matrix representations we've done so far, the matrix size, square matrix, and all of odd size, and that's a consequence of the n eigenvalue having allowed range of 2L plus 1, right? So necessarily odd numbers. Okay. So now the obvious question arises: can you have a matrix representation with the same commutation, or the equivalent commutation relations as the operators, the matrix equivalent of the commutators that we did for the odd matrix size? But can you do the same, but for having matrices that are of even size? Like n by n matrices, but the n is now an even number. Can that be done? Is the recipe that we were using here, using these spherical harmonics, is that recipe to generate the equivalent, the matrix representations? Is that too restrictive? Like, is it? It's giving us these odd matrix representations. So if we don't use this, we use some other way, can we, and here's the question, can we find matrix representations where the matrices have even size? They're square matrices of even size, n by n, but n is even. Can that be done? Well, and that those matrix representations, 2 by 2, let's say, in the simplest case, can we choose 2 by 2 matrices, representations of the operators L squared and LZ and LX and LY, such that the algebra for the operators and the algebra of these 2 by 2 matrices are the same, equivalent? Well, it can be done, and I'll just throw it at you. Here are 4 2 by 2 matrices that do have the same algebra, as the operators. They are the 2x2 matrix representation of the operators. You know, L squared, Lz, Lx, Ly, hat. Okay, and here they are. So for Lx, it's h bar over 2, diagonal 0, 0, 1, 1. So, well, I won't read more, rather boring. I mean, you can just see for yourselves. Okay. Now, if you take the commutator, say of Lx and Ly, you'll get just the same, the equivalent result you would get if you had taken the commutator of the operators directly. Right? And so you get, here are 4 matrices that obey the same kind of commutator relations as the operators directly. So it looks as though we've got a 2x2 matrix representation of those operators. Now, starting with this, we can do a lot. And this is why talk about all this? What's the point of talking about even-sized matrix representations? Well, given the context and where we're going, this is a lead-in to the notion of spin. And spin is related to angular momentum, but it's a bit different. It's not the angular momentum of the type, if you think classically, vector r cross vector p. It's not an r cross p type angular momentum. It's unique to itself. It's something that's uniquely quantum mechanical. It doesn't exist in classical physics, and it's sort of hard to imagine what it is. But its quantum mechanical properties, the matrix representations of spin obey the same kind of relation. They have the same kind of relations as quantum mechanical ordinary angular momentum operators like L squared, Lz, Lx, Ly. Okay, so till next session.